So, we will be discussing another mechanism of strengthening, which is solid solution strengthening. This particular mechanism arises because of interaction between point defects and line defects. So, it is in effect it is interaction of point defects and dislocations. So, we are talking about solid solution. So, the first thing that we should understand is that there are two types of solid solution, and we have already covered the types of solid solution in part 1. We will just look at it to understand with how they will affect the the interaction. So, the solid solution can be interstitial. For example, in when we have carbon or nitrogen in iron. Or it can be substitutional. When it replaces one of the lattice atoms, for example, copper in nickel. So, now these are point defects. Why do these point defects interact with dislocation? So, the idea here is that whenever you have a point defect, whether you are talking about interstitial or substitutional point defect, they create a distortion around them. So, around that point defect there is a distortion created. Now, this distortion interacts with the stress field of the dislocation, and therefore, you have something called as interaction energy. So, and this may and you would see why I have written may, because there are conditions where this may not actually interact, may interact with and this interaction may raise or lower the overall elastic strain energy of the crystal. So, first thing is that this change can be termed interaction energy. So, I am sorry, the change in the elastic, the overall strain energy, that is called the interaction energy. So, this change in energy is termed as. So, we have two types of solid solution, interstitial and substitutional. Interstitial, for example, in the steel, carbon and nitrogen go into the interstitial sites, they do not replace iron from its position. Substitutional, for example, copper in nickel, where copper replaces nickel atom, and even otherwise we get even nickel in copper. So, nickel replaces copper. So, these are the two types of point defects. Now, why do point defects cause strengthening? The first thing is that whenever there is a point defect, there is a distortion field created around it. Now, this distortion field will interact with the stress field of the dislocation, and this causes a overall change in the strain energy of the lattice. So, when the change in the strain energy is negative, it implies that the two are bonding. When the strain energy increases, it means it is a repulsive, or the overall energy of the system has increased, and this change in energy is called the interaction energy. So, this is what I have written here. distortion is created by point defect, and this may interact with the stress field of dislocation and may raise or lower the overall elastic strain energy of the crystal. Now, this change in energy is termed interaction energy. Now, if EI is large and negative, now what will that mean in terms of energy? If it is something is large as well as negative, if EI is it means that the two defects, the point defect and the dislocations have bonded very well, and therefore, you would need some additional energy to break the bond. What will be the amount of work required? It will be equal to EI. So, EI is the interaction energy, which is the amount by which it changes, and the same amount you must apply by additional work to separate the two. And how would you apply that additional amount? You will have to apply it through most likely by stress. So, it means that increased stress will be required for the dislocation to move. Now, we can explain this, we can understand this interaction energy with the help of a simple model. In this particular simple model, what do? We assume that the overall crystal is a continuum elastic, follows the continuum elastic model, meaning we are not assuming a discrete atom like structure, but that there is whatever property we define for the bulk is there uniformly across the bulk, whether you go at the nanometer level, angstrom level or picometer level. So, at each and every level you have a continuum of material and each of them display the same property. Now, with that model we will assume that there is a hole in the model, and what is the size of the hole? Here we will assume that there is a hole and a sphere of another radius is being inserted. So, the hole has radius RA and volume VH. This is in the matrix, and if we are talking about interstitial or substitutional, either way another atom is being inserted over here, and what is the distortion created? We will assume only because of the change in the size, not because of the modulus. We will say that it is the distortion because of the size, and therefore, the size of the sphere that is being inserted will be assumed to be a little different. How can we say that, or how would we take that mathematically? We will say that the size of the sphere that is being inserted has a radius RA 1 plus delta. So, a sphere of radius RA 1 plus delta and volume Vs is to be inserted in the sphere, in the matrix. Clearly, the sphere has a different radius and the hole is of a different radius. Therefore, a distortion will be created. Now, delta can be positive or negative. Positive meaning you are putting or substituting or maybe interstitial atom are larger than the location over there, When delta is smaller in size, then it would mean that you are substituting a atom smaller than the matrix atom. So, that way we will be able to accommodate into this equation whether we are putting larger atom or a smaller atom. Now, based on this we can say the misfit volume, meaning how much is the overall change in the volume when the two are separate. Okay. Right now we are not assuming any elastic deformation for either the ball or the hole. Just as it is, what is the misfit volume? So, we will give misfit volume which is as V misfit, which is nothing but Vs minus Vh is approximately equal to 4 pi R A cube delta. This will be when delta is much smaller. So, what we are doing is basically 4 by 3 pi R cube. Here R will be R A 1 plus delta cube, here 4 by 3 R A cube, where R A is R A. So, this will be in effect 4 by 3 pi common and R A 1 plus delta cube minus R A cube. Now, here if delta is very small, then 1 plus delta cube becomes 1 plus 3 delta, and therefore 3 by 3 and 3 in the denominator cancel out, and what you are left with is only 4 pi R A cube delta. So, this is the misfit volume, assuming that there is no elastic strain right now, or there is no elastic deformation for the hole or for the sphere. Now, because we are defining this, we can now say that delta is equal to 0, greater than 0, it implies larger solute atom, just like I said few minutes back. And when delta is less than 0, it means that the smaller solute atom is being added. On inserting sphere in the hole, Vh changes by delta Vh. Okay. So, now we will assume that the size of the hole is being changed, because now we have this extra sphere over here and there is a hole in the matrix. So, you put the sphere of a different size into the matrix, and the change in that matrix would not be exactly, or the new volume of the hole would not be exactly equal to the volume of the sphere that you have put in there, because there will be elastic deformation. So, the new volume we would say is equal to Vh. So, the change is actually delta Vh, Vh was the original one. So, changes by delta Vh to leave a final radius RA 1 plus epsilon. You see that the new radius that is being defined for this hole is not 1 plus delta, but 1 plus another quantity epsilon, and there will be some relation between epsilon and delta, because it will depend on their compliance, how much is the elastic modulus of the material and what is the nu and so on. So, this is the new radius of the hole RA 1 plus epsilon, and therefore, if we define delta Vh, which is how much the volume of the hole changes, then it can again be written like 4 by 3 pi RA cube, just like I said for earlier, it will be 1 plus epsilon cube minus 4 by 3 pi RA cube. And again this is epsilon is very small, 1 plus epsilon cube becomes 1 plus 3 epsilon. So, all the quantities get cancelled and this only 3 epsilon gets multiplied by this, and therefore, what you are left with is 4 pi RA cube epsilon when epsilon is very small. So, we are assuming that whenever we are inserting a substitutional or interstitial atom, they are not very different from the available space size. Now, we need to find a relation between delta and epsilon, and what we have assumed, just keep in mind that G, the modulus for the sphere and the hole are same. So, G, which is the modulus of sphere and matrix, are same. Therefore, we will not, in our equation will not get the G term, they will get cancelled. What we will be left with is only nu, which is the Poisson ratio. Now, this can be shown, we are not going into the detail, but at equilibrium how would you obtain this? Basically there should be a equilibrium. What would be that equilibrium? At equilibrium, inward and outward pressure on sphere and whole surface must be equal. So, let us say that the sphere is larger in size and the hole is smaller in size. So, when you insert, there is a pressure inward onto the sphere and there is a pressure on the surface of the hole on outside. Now, if you want to equate this, which will be equated by calculating the strains and the stresses acting onto it. So, the pressure term on both the things will have to come out same, and from there it can be very easily shown that delta VH will be equal to 1 plus nu by 3 1 minus nu. This is basically coming from the pressure term into V misfit. Now, V misfit and VH we know are in terms of delta and epsilon. So, we have a relation between epsilon and delta. So, delta is the actual difference in the size and epsilon is after it has been fitted. Now, let us look at a few more things. If we were talking about infinite matrix, then the total volume change because of this one insertion would be equal to delta VH. Okay. But we are talking about small region plus the constraint that the outer surface there will be some bulk. So, the outer surface the stresses must equilibrate, and when you use those constraint what we get. Now, this part is beyond the scope of this work, we will not be proving it here in this particular course. We will just write that actually the total volume assuming these constraints would equal to delta VH 3 1 minus nu while if we were considering, if we considered infinite matrix, change in volume would be equal to, because of this sphere being inserted in the hole, will be equal to delta VH. This is what we calculated delta VH earlier, which is equal to 4 pi RA cube, 4 pi RA into 1 plus 4 pi RA cube times epsilon. So, this is what we obtained, or this is what we know earlier, but we are saying that in under the constraints actual volume change is equal to delta V total, and this delta V total can be written in terms of delta VH 3 1 minus nu by 1 plus nu. Again it is the pressure term which is coming because there has to be stress relaxation. So, this term that you see over here is because of pressure. So, delta V total, the actual change that will come under these constraints is equal to delta VH times these. But what is this term? We know from earlier, this is equal to V misfit. So, this is equal to V misfit. So, you see that we started with V misfit, which is when the two things are separate, and in the end we see that the actual volume change is also equal to V misfit. So, if one had made a erroneous declaration at the beginning that since the volume change between the sphere and the hole is V misfit, so all our calculation should have a total volume change of V misfit, that would end up being the same, being the correct, because we are at two places we are cancelling out the pressure effect, and therefore the total change in the volume comes out to be V misfit. Now, if we want to calculate the interaction energy, then it can be given as P into delta V total, pressure into volume, that is whatever pressure additional pressure is acting on that small amount of volume, that is the interaction energy that is the change in the overall strain energy. But what will be the pressure term equal to? The pressure term will be equal to minus 1 by 3 sigma xx. So, let us say this is a matrix. So, therefore, there will be this will be a tensor quantity. So, these will be the 3 terms sigma xx plus sigma yy plus sigma zz. So, this is the interaction energy between defect and any other defect. Now, if it happens to be a dislocation, then this will come from a dislocation. So, what will be that sigma xx, sigma yy, sigma zz of a dislocation? You will have to calculate the misfit. Now, where do we calculate this pressure? So, now let me first. So, at up to this point, what we have talked about is interaction of a defect with anything. It could be any other defect. Now, we will go into interaction of defect with dislocation. We will invoke the properties of dislocation and put in over here. So, what do we need over here? So, first thing we want is where do we calculate the sigma xx, sigma yy, sigma zz? Where do we calculate pressure? Because you have a dislocation at different points, you have different sigma xx, sigma yy, sigma zz. So, when we are talking of interaction of dislocation and point defect, we want to know how do we calculate or where exactly do we calculate these values of sigma xx, yy and zz. The answer is at the location of point defect. So, let us say if this is a dislocation line over here and there is a point defect over here. So, you have to calculate the sigma xx, sigma yy, sigma zz because of this dislocation at this particular point. So, sigma all the xx, yy, zz, xyz. So, whatever is the xyz with respect to this dislocation at this point is what you have to calculate to be able to find the pressure acting onto this point defect, and then you would be in a position to say what will be the EI at this particular point. So, now what we need is, so this is from dislocation. So, now what we need is the stresses from dislocation. Now, if we are talking about the stresses from dislocation, we know that there will be two types of dislocations. One will be the edge and the other would be screw dislocation. What is the stress matrix for edge dislocation? It has while on the screw dislocation we have something like this. Therefore, we will have pressure which is equal to we will have some finite quantity over here. In fact, you can easily show that this will for a stress for a edge dislocation, this will come out to, and like I said, these terms that you see 1 plus nu, 1 minus nu, these come when we are talking about pressure. So, this is the pressure term that we have when we are talking about the edge dislocation, where you can put x and y for a particular point defect which may be x and y distance away. For a screw dislocation, what will be pressure? All these terms are 0. These are the terms that we use to calculate pressure. So, the pressure is equal to 0, which would mean that EI would be equal to 0. So, the substitutional defect that we are talking about here, that one will create a pressure equal to 0, and hence the interaction energy for a substitutional defect does not interact with screw dislocation. So, that is the fact that we learn and see in mathematical terms. So, the substitutional defect gives a pressure 0 and therefore, EI is equal to 0. On the other hand, substitutional defect can interact with edge dislocation, because edge dislocation has a pressure term, and therefore, this will be a finite quantity and which we can further calculate like this. So, you can say that EI is equal to P delta V, which is equal to P V misfit. So, we will have P misfit equal to 4 pi R A cube delta, and the P term would be 2 by 3 1 plus nu by 1 minus nu G B by pi sin theta by r. So, sin theta is with respect to the dislocation. So, let us say this is the particular point defect we are talking about, and this will be the x and y with respect to this. So, this completely explains the terms in the equation, this particular plot, and we will have an equation like this, which can be further simplified to something like this. So, here earlier we wrote in terms of x by x square plus y square. So, which can now also be written as sin theta by r. So, this is the equation of interaction energy of interaction energy of substitutional defect with edge dislocation. Now, we can further see some important results with respect to this edge dislocation. Now, let us say this epsilon is greater than 0. Then what do we see? That EI, so if epsilon is greater than 0, all the quantities here are positive as long as theta is on the top half of the plane. So, if theta is between 0 to 180, this term remains positive and everything remains positive. So, EI is positive for sites above slip plane. On the other hand, EI is negative for sites below slip plane. Let us see what is the meaning of this. So, when is epsilon greater than 0? It means you have a larger substitutional atom, and when that is the case, EI is positive for sites above the slip plane, meaning there is no bonding. When EI is negative, it means there is bonding. So, the larger atoms like to bond on the lower side of the slip plane. So, they will like to go somewhere below the slip plane. Now, let us look at the other scenario when the substitutional atom is smaller in size. So, here bigger in size and here so when epsilon is less than 0, EI is negative above slip plane, and EI is positive below slip plane. So, now what do we see here? If you have a defect which is smaller in size than the substitutional atom than the matrix atom, then energy is negative for above the slip plane, meaning those smaller atoms would like to segregate on the top side of the or above the slip plane, and on the bottom side it is positive. So, there is no bonding and it will like to move away from over there. If I could simply draw a simple structure, let us say this is a edge dislocation, and let us say we draw certain now let us say I put a small atom, then where does the small atom want to go? The small atom wants to go somewhere over here. So, it would like to go over here, this is a smaller atom. Now, if it were a bigger atom, then that bigger atom would like to go over here. So, this is also very obvious, as you can see that larger atom will like to go in region where it has, where there is tensile stresses, because it itself will be creating compressive stresses. So, that will cancel out. On the other hand, smaller atoms will go in a compressive region because it will create a tensile stress. So, they will cancel out. So, that makes sense. Now, that is for the substitutional atom. How would it be different when we are talking about interstitial defects? So, will the overall equation or the form of the equation for the interstitial defects would be a little complicated. So, we will not be able to derive all of it, we will just understand what is physically happening. So, let us say we have a octahedron in a BCC. So, this is BCC. So, there is one atom over here, one atom is over here, and now let us connect these. So, you can see that approximately an octahedron is created. Now, you can have an atom over here. Now, what are its nearest neighbor? So, this is our which is octahedral site. What else do we know about this? That this will create asymmetric. Now, let us see really if it is asymmetric distortion. Let us look at the nearest neighbor for these this particular atom. So, let us mark A, B, C, D. Let us mark these as E and F. So, which are the nearest neighbors for this particular defect? It is A or E and F, A, B, C, D or E and F. So, as you will see that the distance between these two is actually root 2a, while the distance between this is a by 2. So, a by 2 is smaller. So, the nearest neighbor is actually E and F, which is at a distance a by 2, and A, B, C, D are actually a little bit further away, which is a by root 2, and therefore, this you can as clearly see that this is asymmetric. Now, if this is asymmetric, now if that would imply that it has more space over here in the region from over here, while it has lesser space in this particular region. And therefore, it would mean that when it tries to push a large, let us say this interstitial atoms was a little bit larger in size, more than the space available. So, a large interstitial which will be more than a minus 2 r produces distortion. Now, it will first displace the nearest atoms which are E and F by displacing E and F more strongly than A, B, C, D, which are the next nearest neighbor. In fact, you can calculate what would be delta XX, delta YY, delta ZZ. But what is more important is that because of this asymmetry, it creates a shear strain. And now if it is a shear strain, then it means it can interact with edge dislocation, it can also interact with screw dislocation, because screw dislocations earlier we saw they do not have pressure term or the hydrostatic terms, therefore, they were not able to interact with the substitutional. But interstitial defects, because of their asymmetric distortion, they create shear strain, and this shear strain is able to now interact with the screw dislocations, while edge dislocation interaction is still there because the pressure term is still there. And therefore, and here what you would get in effect is you will still get a relation which is of the form E interaction which is equal to 1 by over r f theta, just that this theta f theta term would be very complex. So, as a summary we can write so, let us say when we are talking about interstitial defects, then this is interacting with both edge and screw. What about the substitutional defects? It interacts only with the edge dislocation and not with the screw dislocation. So, which one would you expect to be stronger? So, this will be stronger strengthening effect, relatively weaker effect is what you will observe over here. And in fact, this is how it has been observed. People have seen or calculated for the delta sigma, which is the approximate change in the strength with change in percentage concentration. So, people have seen that something like carbon, which is interstitial, or nitrogen, which is also interstitial, the effect is much more pronounced. On the other hand, so this is carbon, this is nitrogen. On the other hand, if you look at the substitutional atoms like vanadium, niobium, silicon, so they have, these are the substitutional atoms, they have a much smaller straining effect. So, here you are changing the concentration and the amount of change in stress or the yield stress that you observe. So, here clearly atoms like carbon and nitrogen which go in the interstitial site, because they are interacting with both the edge and the screw dislocation, are giving more strengthening effect, while atoms like vanadium, silicon, niobium which go in the substitutional site substituting the iron atom, over there they do not give as much strengthening effect. So, we have looked at the strengthening effect because of the interaction of the point defects and the edge dislocation. So, we will close this chapter here. Next time we will come and look at another effect which is created because of the presence of point defects, and again it is, we will start actually somewhere where we left, which is that the EI is equal to f theta by r. So, we will start from there, because of that we will see some more interesting phenomena taking place, particularly the yield point phenomena. So, thank you, we will see you in the next module.